Our objective is to make a bottle rocket that can remain airborne for as long as possible while protecting our payload, an egg.
The rocket's flight relies on water and compressed air. Pressurized air forces water out of the nozzle, generating impulse, which is the force applied over time that changes the rocket's momentum. The greater the impulse, the higher and faster the rocket will travel. The amount of water, or water fraction, affects the thrust and impulse. More water generates a stronger initial thrust but adds weight, while too little water results in too weak a push. For maximum impulse and flight height, the water and air needs to be balanced to optimize both force and weight.
To maximise the rocket's directional stability, which is the bottle's ability to maintain its original direction regardless of external factors, we tested different fin designs on Unity, adjusting their area, aspect ratio and placement. Fins resist unwanted yaw and pitch motions, and their position relative to the rocket's centre of mass is crucial for stability. Larger fins create more stabilising force but can overcorrect, so we placed them behind the centre of gravity to ensure the centre of pressure stayed below it. We experimented with different parachute diameters on Unity to optimize the descent speed. The terminal velocity is the constant speed a body falls when the drag forces, air resistance, equal the gravitational forces causing the object to fall. Large parachutes produce more drag in descent, so terminal velocity is achieved sooner, and the rocket descends to the ground slower. Too large a parachute, however, would take longer to deploy and make the rocket heavier. Too small, and the effect of the parachute would be minimal. A fine balance between how long it flies versus how long it glides.
We used Excel to analyze how varying the water-to-air ratio impacted thrust and flight time. The analysis showed that a 0.3 water fraction provided optimal thrust for a strong ascent without adding too much weight. CAD software allowed us to model the rocket structure and design 3D printed components, including the fins and nose cone ring. The nose cone ring positions the cone during the ascent and ensures it falls off at the apex. We simulated the effects of different fin configurations on flight stability. Unity simulations conducted in a virtual wind tunnel helped us determine the ideal fin size of 100 centimeters square and of an aspect ratio of 0.9. Launch conditions aren't predictable. Unity allowed us to get rough estimations of how our rocket would fly under more turbulent and windy conditions. The rocket's construction will also largely affect the rocket's performance. Therefore, we used a lower build quality in Unity to better represent the real world.
Our main takeaways from this are, no matter how hard we try, external factors like weather will always play a massive role in our success, so it's important to try and accommodate them. CAD allows us to visualize our ideas and conserve time. Simulations are vital to all engineering projects where very little practical testing can be done, especially over such a short period of time.